Good afternoon, everyone. My name is Rhea, and I am a PhD student working under the supervision of Professor Enda Cummins in the PROTECT project. My research project is to assess the increased risk from mycotoxins in bovine milk and milk products under a climate change scenario. Today, I'm going to be presenting a feed to food chain risk assessment framework model under a climate change scenario. Mycotoxins are naturally synthesized toxins produced by fungi under favorable conditions. They commonly occur in food and feed products. Exposure to them can cause mycotoxicosis, which has varying degrees of severity. There are quite a few mycotoxins out there, with many considered of toxicological importance to humans and animals. Some of these mycotoxins are regulated by food authority bodies. These are aflatoxin, ochratoxin A, deoxynivalenol, fumonisin, zearalenone, T2-HT2, patulin, etc. for different food and feedstuff. Fungal invasion is dependent on a number of factors including temperature, type of crop, rainfall or the lack of it, insect damage, etc. Amongst these, some are weather variables, which have been predicted to change under climate change situation. The warming of the globe is expected to increase the risk of mycotoxins produced from these fungi, and the risk of mycotoxins is expected to increase in Europe. The spread of aflatoxins is a major concern, and as predicted by Bartolini and Associates, there is expected a substantial increase in risk of aflatoxin in the Mediterranean, Central, and Southern Europe under a climate change scenario. Currently, food safety regulations set by EFSA set a cap on the maximum limit of the presence of these hazards in food and feedstuff. With the expected increase in mycotoxins, food wastage and therefore economic losses are also expected. The EU dairy industry produces around 172 million tons of raw milk. Amongst that, the European Union is also one of the largest consumers of dairy products, with over 45 million metric tons of dairy products being consumed. Keeping that in mind, a feed to food chain risk assessment framework model was developed for the dairy industry. Varying factors affect the initial concentration of mycotoxins in animal feed. These include temperature, irrigation or rainfall patterns, insect damage, crop tillage, crop rotation, soil contamination, pre-harvest. Post-harvest crops meant for feed are either fed straight to the animal or processed or stored for future use. The different processing steps, such as cleaning, sorting, and milling, have been shown to have an effect on the mycotoxin concentration levels in the different fractions. For example, during the milling process, most of the mycotoxin is concentrated in the outer fraction, which ensiling procedures and storage have been noted to have an effect on the concentration levels if improperly done. There is a change in concentration levels, such as the introduction of ochratoxin A, an increase in aflatoxin, or the contamination of the feed by patulin post-harvest, has been noted. In fact, Medina Magan have also investigated the effects of temperature, water activity, and carbon dioxide levels on the growth of fungi on stored grains and biosynthesis pathways and production of mycotoxins. Although these studies have been done in vitro, Bovine exposure to mycotoxins is dependent on the rate of feeding, which depends on the yield expected from the farm, lactation date or time, nutrient requirements of the cattle, feeding practice, and feeding practice of the farm. That is, whether it's indoor or outdoor, which is grazing. Mycotoxins consumed may be converted to less toxic products in the rumen and can be absorbed or excreted into urine and milk. Aflatoxin B1, for example, is converted to less harmful or toxic products, aflatoxin M1, aflatoxin Q1, and aflatoxicol in milk. The carryover rate of uh, aflatoxin ranges from not detectable to 6.2% in some cases. Some studies have linked the carryover of aflatoxin M1 in milk to be related to the milk yield. Carryover of other mycotoxins such as deoxynivalenol, fumonisin, zearalenone is almost negligible, while OTA gets converted into a less toxic metabolite, ochratoxin alpha. Milk undergoes several processes prior to reaching the consumer. Mycotoxins are heat stable and therefore difficult to destroy in traditional dairy processes. During cheese making, certain studies have found that the concentration factor cheese of aflatoxin M1 in cheese to that in raw milk is as high as 5.5. While it is suggested that fermentation of milk to make yogurt can reduce the concentration of aflatoxin M1 in milk. However, for the purpose of this risk assessment, and since climate change variables like varying temperatures have no effect on the stability of aflatoxin M1 or mycotoxins in milk, exposure to humans will be calculated based on the final concentration in raw milk. This, however, is influenced by changes in dietary preferences, which are difficult to project at this point, and therefore Changes in dietary preferences will not be considered for the projections. Climatic conditions affecting the initial concentration and changes in concentration will be analyzed for the purpose of the risk assessment. The model will be built on data available from literature. A sample data form where the type of feedstuff, the temperature range of mycotoxin production, carryover rates, growth rates, production rates, feeding patterns in the country, as well as contamination data, if available, and mean daily intake of milk for that country will be considered. The body weight of the average body weight of the population will also be taken to build the exposure assessment model. Exposure assessment will be carried out on at risk. In the current slide, an exposure assessment was carried out using the data available from the sample data form. An initial concentration was taken from a sampling done in 2012 for Irish maize. The average daily intake for the Irish population was also used for this exposure model. The exposure is only representative of a scenario where the maize is contaminated. Current models which have carried out a feed to food chain risk assessment of mycotoxins in dairy include Coffey et al., which was who carried out the risk assessment in Ireland, Signorini, who carried it out in Argentina. Signorini utilized the equation for milk yield, while Vandervelde's clerks assessed the impact of climate change on carryover of aflatoxin B1 from imported maize to aflatoxin M1 in milk produced in Netherlands. They utilized Batlini's aflamase model to predict mycotoxin under a climate change scenario, as well as crop phenology models to assess predicted changes to fit into the model. Finally, different carryover equations, yield, lactation dates, etc. were utilized in the model. Vanderpeer integrated risk assessment and climate change scenarios to assess the increased risk of mycotoxins in tomatoes for Spain and Poland in a farm to fork scenario. A feed to fork risk assessment will be carried out under different climate change scenarios. This model will be based on data collected from literature and will be for the risk of mycotoxins in dairy